Right, so yeah, starting recording now. Cool. Thanks for confirming that you see it. So today I want to, walk you through an interesting research by Google, which is the BERT model. So we had two previous sessions in the past. One of them was about transformer in depth, where I walked you through these slides, and then the other one was about applications of transformer, where we went through a application of transformer which was an English to French translation. So today I want to go through another important paper, which I don't know how often the BERT model is used nowadays. I mean, it's useful, it's powerful, but everyone seems to be talking about GPT-3 and ChatGPT, etc. But I believe it's still useful. First, practically, and second, and most importantly, by just seeing how the idea of the model and how it works, and as an interesting application to the transformer architecture and how to use it in practice. Yeah, so just before I start, let's go through like a quick review of the architecture again. Just a couple of minutes. You may already know it, but just in case some listeners not know it, especially over YouTube. So, transformer architecture is an encoder and decoder architecture. So you have an encoder here which takes an input representation and converts it into some form of hidden representation, and then a decoder which takes that hidden representation and generate an output. And we talked previously about the embedding and then encoder, decoder, and the attention, which is like the core of the transformer architecture. The paper, in fact, is called "Attention is All You Need," and then the different parts. I'm not gonna spend a long time on this, and for those who are interested in learning more, I can refer you later to a previous video. But for now, I want to just remind you about something quickly. So we talked about in that previous presentation where we talked about the idea of the sequence to sequence in general, whether not necessarily sequence to sequence, but the recurrent neural network. That's the previous idea and how they work. And you could have like one-to-one, one-to-many, many-to-one, etc., and then a transformer which kind of like replaced this with an encoder and decoder. And then we talked about the configurations of the applications of transformer. Transformer has an encoder and decoder, but you don't have to use them both. And so, for example, you could use the encoder only for applications like sentence classifications, NER, etc. Or you could use the decoder only if your task is for generation. So generative AI, requires, the application of transformer to generative AI requires only the decoder, because you don't have anything to encode to start with. You're just generating things from scratch. Or you can use them both, like we did in the previous presentation, where we implemented an English to French translation. So in this presentation, we are going to talk about an encoder only example, which is the BERT model from Google, and it's a pretty effective one. Now, the good thing is that if you go through the BERT paper, which I actually encourage you to go through it, you will realize that there isn't a lot of there isn't like a new invention with regard to the transformation. They are just using the transformer model as is. They just specify 12 layer, for example, for the smaller model, 24 layers for the bigger model, etc. But the architecture is exactly the same. This architecture you see here, obviously just a decoder. Just the encoder. The decoder is for generation, and BERT is just an encoder only. So the architecture is the same. The innovation is how they actually used the transformer architecture. And if you go through the paper, you will see that the title itself actually raises a question of pre-training of the bidirectional transformers. So question comes to mind is like, what do they mean by bidirectional? And initially, the first answer is that because they are using a transformer architecture and it has attention, it has self-attention, so you know that every single token in a source statement kind of like attend to every other token in the same sentence. So that's kind of can be thought of as part of what they mean by bidirectional, which is true because of the attention. But they actually have another interesting idea that they implemented, which is called a masked language model. So there is like the game of well, I don't think it's called a game, it's more like the closed task, where you could have something like let me just open some window here for. So this comes in schools and language examination, where you could say, for example, the student went to and then you try to guess that, and you would say, well, most likely went to the school. That's at least one option, and that's called a closed task. And inspired by it, they thought, the researcher from Google thought it's actually a good idea to teach a model how to understand statements is by trying to teach it on what they call a masked language model. So they take a corpus essentially and mask percentage of it, and we will see the numbers later, and they try to train it to guess the original tokens. And obviously the fact that it learns to guess it means that it's actually understanding the whole input statement, otherwise it wouldn't be able to guess it correctly. And then you might be wondering, like, why are they doing this exactly? Like, obviously in an NLP model you would want to have a model that is more useful than that. I mean, sure, that's an interesting use case here where you try to fill in the blank essentially, but that's only one task. But in fact, the idea, what they are trying to achieve here, is that they want the model to actually be able to understand the statements. And that's one way of achieving it, by training it on large corpus. And now they have a model that has a good understanding of the language, and then they can fine-tune it the way they want to the application they need. So if you look at the paper here, initially they kind of like they try to motivate it by saying they talk about the fine tuning, which trying to find where they talk about it in the paper. Yeah, so they have like two steps here, where the pre-training here is essentially trying to cheat the model as much as possible about the language, and then after that they fine-tune to the individual task. So this is kind of like the whole idea behind what they call the fundamental modules which are large enough that they have good understanding of the whole task. Well, the whole thing. That thing could be like computer vision or language NLP, etc., and they could easily fine-tune it quickly, and we will see that in a demonstration later today. And they could then just fine-tune for the task they need. So that's one thing they did, which is the masked language model trying to guess. And let's see how they actually do it. So they mask 15% of the tokens and try to guess them. So they take, obviously you can't just manually mask certain words, so they just take things randomly and they just mask them and try to use the model to guess what the right word is. But they also they try to change it a little bit, because one thing is that the mask is a special token that they add, and that mask is only available in the pre-training stage. It's not available, when you are inferring or fine-tuning. So they essentially have this problem where a downside is that we are creating a mismatch between pre-training and fine-tuning, since the mask token does not appear during fine-tuning. That's what they say. And to work around that, what they do instead is that 80% of the time they take a random token and mask it, and 10% of the time they keep it unchanged, and then the other 10% of the time is that they replace it with something random from the corpus. So a wrong statement, essentially. Like in this example, it could be the student went to the moon, for example, which is obviously wrong in this. I mean, it is possible, but unlikely. So that's how they go about the first task, which is called the masked language model. Now, that's obviously gonna put you in a situation where your model is able to understand the context of and the relationship between a different word, but that's not necessarily enough. I mean, obviously you might be able to understand words and how they're related, but if you want to better understand language, it's super powerful if you're able to tell or predict whether a statement is related to a previous statement. So that's the second task they train it on. It's kind of like making it even more, giving it more awareness of what a language means, and that what a statement in a language means by, not means, I don't know what the right word here, but how the statements of a certain, say, paragraph are related to each other, not just how a certain word is related to its surrounding. So that's the next task they train, which is they call next sentence prediction. So what they do is that they take sentences from the corpus, and 50% of the time sentence B actually follows sentence A. So if we take this paper, for example, you could say that, let's take this statement here. Unlike Peters et al., etc., we do not use traditional left to right or right to left language models. And then that's sentence A. And then sentence B is instead we pre-train BERT using 2 unsupervised tasks, etc. So this statement is likely to follow. I mean, if you don't know the paper, if you haven't read this paper and you see this statement, it does actually make sense that this sentence follows this sentence. But for example, if you take this sentence, unlike etc., the same sentence, and then put, this statement here, for a given token, its input representation is constructed, etc., it doesn't make sense. This statement is not related to this one at all. So that's how they try to teach the model how to guess that a sentence is actually related to the previous one or not. And that's the second task here. And both of these tasks is kind of like what makes BERT very smart about understanding the language. And that's just pre-training. They train it on massive data. I mean, not as massive as maybe GPT, but it's still very big actually. So they use the book corpus dataset, which is 800 million words, and they also use the English Wikipedia, which is 2.5 billion words. So that's a massive corpus in total. And for a model to have an understanding of that kind of level of or size of corpus, you would hope that it's actually become smart in language, and it is actually smart. Now after that, let me see if there's any question. Just one second. Cool. Okay. Yeah, let's go back. Cool. Yeah. So let's go to the other part of it, which is the fine-tuning part. And in this part, they already have the fine-tuned model. It's massive. It's like, they would talk about the number of parameters, but I think it's like 300 million or something like that parameters. Now all they need is that take that pre-trained model and then, whatever task you want. Do you want, for example, sentiment analysis? you can't just take it and do a fine-tuning on it and you get the result, because obviously the model understands language, so all it takes is kind of like to tell it what you want to do essentially. And they go through multiple experiments, they explain them in detail, and they explain how they configure the language, the model. So let's go back to, let's take a look at this graph, this one or the one before. Let's see. So yeah, this is kind of like explain the two things we've been talking about. So you can see that let's look at the pre-training. So that's obviously like something like a masked sentence here, and that is so they, this is supposed to be something like masked here, and then this is supposed to be unmasked. So they feed some data which is masked and then try to predict the unmasked one. Or they could feed two sentences and then see whether they are related or not by trying to take the hidden representation of the C. I think that's stands for classifier. So at the end of the day, it's transform model. So you give it the encoder model. So you give it some input data, it's going to convert it into some hidden representation. So that representation, obviously based, because of due to your training and the way you kind of like feed your data, it's going to kind of represent the statement. And these T1, Tn, etc., they kind of represent the individual tokens. But this C here, which is the correspond to the special token they call CLS, I assume it stands for classification or classify, is going to be, they aim to train it in a way that it's kind of represent the entire sentence or the entire thing, regardless of what that thing is. Is it classification or is it entailment, whether sentence B follows sentence A, etc. And that's going to play a big part here. And so you can see, I think they say here in the so for example in the glue benchmark, to fine-tune on a glue, we present the input sequence for a single Instagram section 3 and use the final hidden vector corresponding to the first input token as the aggregate representation. And then what they do essentially is that they link this vector C into just a feed-forward network that takes hidden size and converts it into K, where K is the number of labels. So for example, if you're trying to build a model that look at Amazon reviews and tell you whether it's positive or negative, then you have two classes, positive and negative, and essentially assume your hidden representation is 512, then you have a feed-forward network or from 512 to 2, and that output is going to give you the result, or whether the review is positive or negative. And let's see, for other tasks, I mean, you could go through the paper. I actually encourage you to go through it and see the experiments here, the way they do it here, and they go through the different benchmark. But essentially it all boils down to kind of like which output you want to use in I think this one might be more interesting here. So let's see this say, my dog is cute, he likes playing. So you can see that this statement that related, and then if you want to train a model to tell you whether they're related, like entailment essentially, then you could use the classification hidden representation. Yeah, so let's talk quickly about the sizes of the model. So you can see there's two models that they have trained, and it's open source, so you can obtain it yourself and play with it. And the base model, which is the smaller one, they made it similar to OpenAI GPT, but that's the GPT one, by the way. That's pretty old. Just for comparison purposes. So it has 12 layers, and it has hidden size of 768, and then it has 12 attention heads, and the total parameters is 110 million. And the BERT large is double the number of layers and bigger hidden size and more attention hit, and total parameter is 380 million. So it's not actually small, it's pretty big actually if you think about it. It's just nowadays small compared to 175 billion from, you know, GPT-3 for example. Yeah, so oh, I want to mention something else. In the fine tuning, so when you want to, if you want to, you know, we're going to see this in PyTorch, but they, what they do when they do the fine tuning is that they, let's see the image in here somewhere. And then for each task, we simply plug in the task specific input and output into BERT and fine tune all parameters. So that's important here, you know, like the model isn't frozen, the model will still adapt. They train the whole thing, so it's not like in this case where they're doing some sort of a classification and they introduced a feed forward network on top of the BERT model. They actually still, you know, fine tune the entire model. They don't freeze the original BERT model. And I assume they have tried both cases and realized this is better, and it makes sense. You want to have some flexibility in your model. So let's go do some coding. I want to show you this, and then we can maybe... Oh, and there's also a section about ablation studies, and what that means is that you have a system, you want to, you know, break down your system and see which components are actually useful and which are not. So they, you know, they try to take, for example, that they only take the masked language model without the NSP, next sentence predictor, or what, I think so. And, you know, try different combination to see like whether, you know, how these have an impact on the model. So I'm not gonna go through this. You can go through it in the paper, but I think it's important. These two sections about, you know, the experiments and the ablation study is interesting to read. But let's go ahead and do some coding here. I did this, you know, it's already prepared. But I could walk through it again and maybe re-execute it. So just want to make sure that I have the model saved because I don't want to repeat the training here. So the model path should be just want to see what the model workspace data. So workspace data base, and then yep, that should be, that's today. Okay. Cool. So I have the model saved. I could restart this so we could, you know, see this together. Restart. Clear output. Okay. So for this, you know, one good thing is that you don't actually have to define the model yourself. You can use the Hugging Face library. It's super cool. It has lots of models that you can use, you know, out of the box. It has lots of data sets. So one of them I'm using here is called the Amazon Polarity. And it's just based on the customer reviews, whether it's negative or positive. So I'm going to show you some samples here. What am I doing here? So this is just loading the data set here and then just randomly printing some positive and negative samples. So here are some positive samples. Studying even for the non-gamer, best soundtrack ever. You can see that's, you know, you could tell as a human, you could tell these are like, seems to be, even though I'm just pasting the title, you could tell these seem to be positive samples, while the negative, like, you know, buyer beware the worst, awful beyond belief, and you could tell, you know, that's pretty negative ones. Why don't I actually show a couple of actual content, not just the title. So let's do positive samples of 1. That's just to give you an idea about the data, how the data looks like. So you have the label here, which is 1 stands for positive and 0 stands for negative. And you have the title and you have the content. And the way I'm going to train this is just to concatenate these together as one statement. Yeah, I mean, you could try to add a separator or whatever you want, but at the end of the day, it's just text. So title and content, at the end of the day, it's just going to give you an idea, regardless of how you look at it. Right. So I have some boilerplate code here, which essentially, you know, boils down to taking the taking text and tokenize it. And good point I forgot talking about, which is that BERT uses, I think it's next I think it's called word piece. Yeah, so yeah, as you know, as we mentioned maybe in the previous presentation, there are, you have to convert your text into some representation, and they use a word piece model, and this one is from Google as well. So if we take this thing here and then word piece from, I think you can find it on, no, it's not on, I know sentence piece is you can find it here, but I don't know about what. I think it's similar. I'm not entirely sure what the difference between them is, but it's going to be similar in nature. The idea is that you want to see the most frequent word, the most frequent subwords, and then kind of like make them as a dictionary, so that you don't have to memorize or have a embedding for every single possible word. Like, you don't have to have two embedding, one for paint and one for paints with S. So they use that encoding, and the good thing again is that you don't have to worry about finding the tokenizer yourself. It's already built with Hugging Face, so you can just use it. And you can see I'm loading here the tokenizer, using transformer, which is for Hugging Face essentially. And then the checkpoint here is BERT based case. You have case, you have not case, etc. So let's actually try that, see how it works. So the tokenizer, let's see, help tokenizer. Oh, sorry, I didn't load it. Let's start. Clear all output. So going through these, and then tokenizer. Let's see how to use this one here. So BERT tokenizer. Does it simply work if I do tokenize test statement? No? Oh, tokenizer. Is that gonna work? Yeah, so you can see it did the tokenizer here, tokenization. It gave you some, these are your tokens, and these, that's I believe is the which statement it belongs to. Because if you recall from the model, I don't know whether I mentioned this in detail, but in the model you could either have one statement, and then you try to, that's for the masked language model, and you try to guess the original statement, or you could have two statements and you have to find the relationship between them. And in the case of two statements, you want to have some sort of mechanism of identifying which sentence this token belongs to. And I think this is what this is about. But essentially, you will just end up feeding these to the model itself, so you don't have to actually play with it, and as we will see later. So I'm taking this, just building some data loader, some Python data loader, so that I can feed them into the model. And then and again, you look, you see how oh, that's gonna take some time. That's fine, we can wait for it. Again, you see how I'm not actually doing a lot of configuration. Like, I'm just taking a model and asking Hugging Face to give me a model for sequence classification. But assume we don't have Hugging Face. You want to understand how this is happening. So essentially, it's something similar to how they talk about the experiments here, where they have the base model, and on top of it they add a layer for classification that take the CLS. CLS hidden representation to convert it into N classes, or in this case K classes. But good thing is that you have it in Hugging Face, so all you tell it is that, hey, give me the model for the base model. I'm not using the large here, so that's the 12 layer model. And then I'm doing the usual training here, so optimizer, scheduler, these are typical in pretty much every algorithm. You just want to tell the model how to train. And then I I want to show you something interesting here. So I did, you know, 5 epochs here in the training, and then you know, to start the training here, you know, use the data loader, move it to the GPU, etc., and then get the output and loss. So this is kind of like, there's, you know, it's not rocket science. You find it in pretty much every training loop, where essentially boils down to getting a batch, evaluating the model, and then doing the loss and backward, etc. So that's nothing special here. But one thing interesting I want to show you here is that I was running this earlier before the presentation, and it was gonna take a long time. I mean, yes, it's fine tuning, so the model is pre-trained. It means that, you know, you can theoretically finish it in, you know, very quickly, but it's not gonna be like a couple of minutes. So I intentionally, you know, stop the model after it trained for, I don't know, like 3%, 5% of the Amazon Polar dataset. So for information, the Amazon Polar dataset is 3.6 million reviews, and I don't know, like even if you do 10, that's like 300 or 300k statement or 360k statements. But I did less than that, and I broke it, and it's just 1 epoch, so I didn't do much here, as you can tell. And now, you know, I saved the model. Let's just do some training here. So I want to learn, you know, load the model from save, because I don't want to do. Okay, well, I don't have it, so let's load it here. So I'm gonna do model torch.load. I think that's it. That's the correct path. And do I need the data? Oh, I need the test data, so I'm just gonna wait for this to finish loading. Should take almost done. Cool. So let's try to load the model I saved earlier. Oh no. So import torch, and then I'll load the model now, and let's try to do some testing on it. So I'm using the test data. I know obviously it's big, so I'm just using, like, let's just do I don't know, 100 samples only, just to find the accuracy. Oh, device is not defined. I think I might have not executed the whole thing. Let's where is it? Where is the device? Oh, it's defined here. Let's copy that line and then define it here, and it's BERT is not defined. Oh, it's called, I call it BERT. Okay, let's call it BERT. And then order dictionary. Not too sure what's happening here. Let's just in case I want to delete the model. I wonder whether there's some clash here. Okay, let's see what collection dictionary object has no attribute model. Oh, what am I doing here? The BERT classifier. Oh, I think I know what I'm doing here. I need to actually use this. I can't just do load, because it might get confused, might not load the whole thing. So I think I could do this instead, and then give it this path, and then let's try it again. Hopefully that will work. Not a valid JSON file. Yeah. Okay, so I think I would need to do kind of like loaded the pre-trained one, and then on top of that add update the weights somehow. So well, I mean we could just do, instead of, you know, going through this, let's just so I'm gonna delete this one here, and then I'm gonna do the training here just very quickly. I'm just gonna leave it for maybe like 100, and then try to see the accuracy of it. Meanwhile, let's see if we have any questions. Um, could you zoom in? Oh, sorry about that. I just saw this one here. That's I wish I saw that earlier. Yes, I can certainly zoom in. Sorry for not doing this earlier. Trying to zoom in now. Is that better now? Also, are the code from this reading week and the previous one? Yes, the previous one I shared the YouTube video and it has a link to the GitHub repository, and this one, yes, I'm going to share it as well. Yeah. So let's stop the training now and see. I'm just gonna interrupt it. So you can see how much did I train? 420. That's not a lot, so it's quick. Let's see how our model is doing in terms of accuracy now. Let's hope it works this time. Okay, it worked. So it did 100. Okay, so you can see that I literally just trained it for how many? Like 420 batches, I think. And then you could see the accuracy is like 91%. That's pretty impressive. So I just took a model, trained it a little bit, and quickly, like you saw, I just do it on during the presentation, which is pretty impressive. And obviously, I think I managed to reach 96% or something like that on the Amazon polarity data. But then let's try to use the model just ourselves. So I built this function to use the model to do some prediction, and then tells you whether it's does a softmax on the output, and tell you whether it's negative or positive. And then after that, I'm just gonna use it. So I'm just gonna say, it's such a great day today. The weather is lovely, etc. And then try to execute it. It was just figured out it's positive. And then this one isn't as positive. Let's see whether it will manage to guess it even with this little training. So this one is obviously it didn't catch it, so you can see it's positive. Well, initially I tried it on more iteration and it did catch it's negative, and you could tell why it's not able to guess it, because there's like, I bought this book for my dad, etc., and then he initially really liked it, and obviously it wasn't smart enough to guess that after that, however, etc. So you can say that this kind of like review itself is a little bit in the middle, where he liked some of it but he didn't like the latest chapters. So but when I trained it with more data, it actually told me that this is a negative review. So let's see if I change it to something like, what's that more, and he did not like it. Yeah, it's obviously able to tell that it's a negative one. But obviously these single examples don't really matter much, but what matters is that given a test data, and obviously we're taking like just 500 sample, but you need to do the entire thing. But being able to tell you how 91% of the time tells you correctly whether that preview is negative or positive is pretty impressive. Yeah, so I guess the question is that could be like, why are we doing this, considering that there's already GPT and 1, 2, 3. I guess, as I said earlier in the presentation, the way they do this is pretty interesting. How they mask the language and try to guess it, and they try to have like two statements for them to guess each other. And the second answer is actually it's not that bad. It's pretty good. So one interesting thing I was doing using BERT previously is I was trying to use it to be able to automate discovery of log sentiment, by just looking at the logs. So for example, I mean, I work as a software engineer. I do a lot of backend services, and it's a bit exhausting to have to look at logs and try to see what went wrong, maybe do filtering by exception or error or fatal, etc. But it's not a good idea. It wastes a long time. So I thought maybe I could train it on logs and just automate it. And I did that. I took that BERT model, and then what I did was I downloaded like a large number of repositories from GitHub. Like these are, I don't know, 10K or something repositories, and then I extracted log statements from them, and whether they are error or warning or info or etc. And then trained the BERT model on it, so that it's now able to see a log and tell you whether it seems like an error log or a warning or an info or a debug, etc. And it wasn't great. I think I achieved like 80 something accuracy, but it's still like, instead of looking at logs yourself, why not just have a BERT model? And then the other thing obviously is that the benefit of such a model is that even though it's relatively small, so I'm doing this training on my GPU. My GPU is an RTX 3090 with a 24 gigabyte of memory, and it's loading, and I'm able to use it, and I'm able to train it on just that GPU. In comparison, I would need maybe like 30 GPUs. I did the calculation the other day. So GPT-3 is like 800 gigabyte just to load in memory, and if you divide it by, I don't know, like the a GPU like mine, I would need 33 GPUs, more like 34, just to be able to load the model. So yeah, it's useful. It's interesting. I would certainly encourage you to play with it. Go to the Hugging Face BERT. Oh, and then there's another thing I want to mention is there is research from Hugging Face. I think it's called Distal BERT. That's like based on BERT, similar architecture, but they tried to come with let's see the goal of it. They tried to make it better, because BERT itself had maybe like some toxic part, etc. I think what these guys did is that they did some kind of cleanup on the data and try to make it better. So that's also worth taking a look at it. But you can start with the BERT one, and it's pretty easy to use. As you can see here, I didn't actually do any kind of model definition myself. I just took it, fine-tuned it, and it's working. Cool. So I think that's mostly what I have to say today. Is there any question or thing to discuss? Okay, I see some question. Hello. I invited you to speak. Mutverik. I don't know that.
Hello.
Hello.
Yeah, so I'm pretty new to this language models,
Mhm.
but so you said like the bird is only an encoder transformer, right? And
Correct.
GPT is only a decoder transformer.
Correct.
So does this imply that bird cannot produce text and GPT cannot interpret text?
Um, Pretty much, yeah. I mean, let me just clarify this a little bit. So, BERT, yes, it cannot generate text, and that's not what it is used for. It's mostly used for things like language understanding, sentiment analysis, name entity recognition, but it does not generate text for you. That's correct. Now, about GPT, it's not. So, you said GPT is not able to interpret text. Is that what you said?
It
Or
implies that, right? If it's
yeah.
a decoder transformer, it implies that it cannot interpret text.
Oh no, no, it can actually interpret text, but the way that it's done is via the decoder. So you can imagine, for example, as a generative model, if you write something like this, where tell me a nice story, then as a generative model, it's able to do some kind of like auto completion, where it take this prompt and it's able to generate based on it. So it is actually able to interpret. It's just not the encoder way of doing it, because the encoder takes something and try to just give you some result about it, some hidden representation, while a decoder based transformer is going to take whatever you said and try to generate more data on top of it. It's essentially an auto completion system, if that makes sense. Does that answer your question?
Yeah, but I've seen some like generative capabilities from BERT. Even the Hugging Facebook, the which like uses BERT, like it also has some like limited generative capabilities.
um can you give an example? Because like it's
For example,
uh-huh.
it was almost able to autocomplete like if I reviews,
Mm-hmm.
and it was even able to translate some things.
so so
What does
that's
not count as
so that must have been like an indirect way of doing it, so not necessarily as generative. So you could, for example, one thing that I could think of is that you have like a powerful encoder that takes a statement and converts it into some hidden representation. Why not take that and add a decoder on top of it to generate translation? That's what I am thinking, of one way. But the vanilla BERT, and I mean, as you can see, it's just takes some input, convert into some representation. It's not able to, for example, take five, just the vanilla BERT is not able, say, to take 5 tokens and generate 6 for you, for example. It's just take 5 and generate 5 hidden representation, and you're free to do whatever you want to do with it. And I think, in fact, I think it's clear. I don't know whether it's this paper or another paper. They say it's not a generative model, at least without modification, without adding architectures on top of it. If that makes sense.
yes,
Yeah,
yes.
but let me actually. I mean, I don't claim to be expert myself in BERT, but let me see if there is any, like, how they might use it in like machine translation. So BERT is on this one. Well, there exists way. So this one is answering this. There's exist way of it can be incorporated into machine translation. It's not an easy problem, and there's, yeah. So you can see here. It's, I mean, obviously we can't necessarily take a Stack Overflow answer as the definite answer, but you can see it's not a translation. But it's not the translation model, which means not a generative model in a sense, but it does seem that people might have found ways to do translation with it. And I imagine, so BERT. So we propose a new algorithm named BERT fused model, in which we first use BERT to extract representation for our input sequence, and then the presentation are fused with each layer of the encoder and decoder of the NMT model. Yeah. So as I thought, basically they take BERT, they do a representation of it, they use it to do encoding, they generate a representation, and then they fuse it with another thing for the decoder to do the actual translation. But on its own, it's not able to generate anything for you. Does that answer your question, or you still have some doubts?
No, 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 no. That answers my question.
Yeah.
Also, one more thing. Like for example, in GPT, the decoder model.
Hmm.
So there's some even then, like if I type something and for GPT to understand what I am like saying, it needs some kind of encoder capability, right? It needs to convert these tokens into a hidden representation for it to understand.
Oh yes, it
No?
it definitely does. So if you look, let's go back and take a look at the decoder architecture. Let's zoom this a little bit. Let's see, trying to. Is there any way to zoom this? I'm not expert with this, but Yeah. So the decoder itself is it has attention layers, and it's able to attend to what have been previously generated so far. So it does actually understand the language and is able to relate different words in a sentence to each other. It's just that the decoder is different in that it only attends to previous data. So that's why you can see that in the language in the decoder you see it's a masked multi-head attention, while in the encoder it's not masked. It attends to everything, the previous and the next, because it has the whole statement. While with the decoder, you use it to generate some data. So you have like 10 words and you generate the 11th word, and then you know feed the model the 11 words and ask it to generate the 12th word for you, and so on. But so it is able to attend, it does understand language, but it only looks backward, it does not look forward. And while with BERT you can see, from the title itself is like bi-directional. Does that make sense?
Yeah, it makes sense.
Yeah. Cool. So we've got like 3 more minutes. Is there any other question? Cool. Well, I take that as a no. And obviously, we have the Discord group. If you have any other question, feel free to post them there. I will upload the recording, and then I will also share the notebook on GitHub for you to experiment with. And yeah, thank you for attending, and have a good day, or afternoon or evening, depending on where you are. And thank you. Bye.